We're going to start our new unit on thermodynamics, which is the study of energy and energy transfer. In thermochemistry, we study the energy changes that accompany physical and chemical changes in matter. Those changes can be classified as physical, so for example, this ice melts at 0 degrees Celsius. As chemical, so various chemical compounds and elements undergo changes in fireworks, and also they could be nuclear. So in the sun, hydrogen undergoes nuclear fusion. We're going to take a look at some terms that you need to know for this unit. So in thermodynamics, we split things into the system and the surroundings. So the system is just the part that we're actually wanting to study. So for example, a reaction mixture in a flask, and the surroundings are everything else that aren't a part of that system. So everything in the universe is made of whatever system we're studying, and then the surroundings, so everything other than that system. A couple examples here. So if fossil fuels are undergoing combustion, they release heat and feel warm. And so that is called an exothermic reaction because heat is released. We'll talk about exothermic and endothermic a little bit later on this week. And in our other example here, we have a cold pack in which there's some chemical and water, and when those two are mixed, heat is absorbed from the surroundings, and so it starts to feel cold, and that's called an endothermic reaction. Once again, we'll talk about exothermic and endothermic reactions in our next lesson. Whatever system we happen to be working with can either be open or closed. So for example, this flask here is open to its surroundings. And so if a gas is being produced, that can end up being released into the surroundings. So in an open system, matter and energy can be exchanged with the surroundings. A closed system, on the other hand, matter can't be exchanged. So whatever is produced is going to stay within the system. And it's only energy that can either be released or absorbed to the surroundings. If you remember in grade 10, we talked about the law of conservation of matter, where matter couldn't be created or destroyed. We looked at chemical reactions and how the bonds between different compounds could change, and we could create new products, new compounds, but that the total number of atoms was the same. And similarly with energy, there is a certain amount of energy in the universe that doesn't change. So energy can't be created or destroyed, but it can be transferred from one substance to another. It can be converted to different forms. So in grade 9, when you did electricity, you probably took a look at renewable and non-renewable sources of energy and looked at different energy transfers at that point. Okay, so some more terms that we need to take a look at before we look at calculating heat. Thermal energy is the total kinetic energy that is in a substance. Temperature is the average kinetic energy of the particles in a substance or system. So we'll take a look at the difference between those two in an example. And heat is the amount of energy that actually gets transferred between substances. We measure that in joules. The symbol for that is just a capital J. And that heat transfer happens spontaneously from a warmer object to a colder object. So if I have a cup of coffee that is 90 degrees Celsius and a bathtub filled with water that is 15 degrees Celsius, the temperature, so the average kinetic energy that is in that cup of coffee versus the bathtub, is going to be higher for the cup of coffee. So it's 90 degrees Celsius. So it has a higher temperature. The bathtub, on the other hand, has a much greater volume of water, and so its total thermal energy is going to be much more than the cup of coffee. So even though the average kinetic energy is 15 degrees Celsius, if you looked at all of the particles that are in there that have that average kinetic energy, overall it would have a higher thermal energy. And for both of these, if you were to leave those for a while, the cup of coffee would end up losing heat to its surroundings and become room temperature eventually, Now the bathtub, I don't know too many people that are taking a bath in 15 degrees Celsius, but that would end up then warming up a little bit to room temperature. So it would end up absorbing energy from its from its surroundings. Okay, so how do we actually measure that change in heat, that energy that's being transferred? So every single substance has something called a specific heat capacity, and that is the amount of energy that is necessary for that substance to change the temperature of 1 gram of that substance by 1 degree Celsius or 1 degree Kelvin. It's measured in joules per gram degrees Celsius. So how many joules are necessary for 1 gram of a substance to increase by 1 degree Celsius? So the amount of energy that's either released or absorbed by a reaction, then we can calculate by Q equals mc delta T. So Q is our heat. Almost wrote energy there. It is type of energy. So heat in joules. M is mass in grams. C is the specific heat capacity, which is over here, measured in joules per gram per degree Celsius. And delta T is our change in temperature. And that is measured in either degrees Celsius or Kelvin. The only important thing is that your final and initial temperatures must both be in the same, but the change will be the same whether you use degrees Celsius or Kelvin. Okay, so let's look at a couple of examples. So how much energy is required to heat 20 grams of water from 6 degrees Celsius to 30 degrees Celsius? So we know that the mass is equal to 20 grams. And that's going to get covered because specific heat capacities, wrong thing. Okay, so specific heat capacities can be found in your textbook on page 280 and also page 743. There's a few different ones on those 2 pages. And then also in the homework that I have posted in the hub, there is a data table on there that also gives some specific heat capacities. Okay, so the mass of the water is 20 grams. The change in temperature goes from 6 degrees to 30. So my final is 30. I started at 6, so that's a change of 24 degrees Celsius. And if I look up in one of the data tables, my specific heat capacity for liquid water, it is 4.19 joules of energy to raise 1 gram of water by 1 degree Celsius. So the amount of energy then that's required for that mc delta T. So 20 times 4.19 times 24, which is equal to 2008.32 joules. And we're probably not going to talk too much about significant digits and scientific notation. I will convert my answers, but if that doesn't make sense to you, then don't worry about that part. Okay, so when we move on, one of the things we're going to be doing is we're going to see a lot of our answers in kilojoules, not joules. So 1,000 joules is equal to 1 kilojoule. But over here, our Q is also always going to be in joules because our specific heat capacities are given as joules per gram per degree Celsius. So if I divide this by 1,000, I'll get 2.008 kilojoules. Okay, so it took 2.008 kilojoules of energy to heat 20 grams of water from 6 degrees Celsius to 30 degrees Celsius. Okay, so that one involved liquid water, and we didn't change at any point to a solid or to a gas. But sometimes our temperature range covers more than one state. And so we need to look at specific latent heat as well. And that's just the amount of energy that's required to change 1 gram of a substance from one state to another. So at that point, there's going to be no temperature change. So for example, water changes from a solid at 0 degrees to a liquid. And so as ice is heating up and coming close to 0 degrees, it will be a solid, it will hit 0 degrees, and then it stays at that temperature until the forces that hold the particles beside each other, not allowing them to move past each other, until those forces are broken and it becomes a liquid. And then at that point, any energy that's being given to the system can then go to raising the temperature of the water. So temperature raises until it hits its melting point, and then at that point, all of the energy is going to break those intermolecular forces that are keeping it a solid. Once those are broken and it's a liquid, then the energy can go to raising its temperature once again. And then that same thing happens when we go from a liquid to a gas. So the two energy changes, so the amount of heat that is required is the latent heat times the mass. So that can be the latent heat of vaporization, which is the energy needed to evaporate or condense. So that's as we are switching between a liquid and a gas, or LF, which is the latent heat of fusion, which is when we are going between a solid and a liquid. So let's take a look at an example that covers multiple states and requires not just Q equals mc delta T for the change in temperature, but also changes of state and how much energy is required for that. Okay, so calculate the amount of heat required to raise the temperature of 60 grams of ice from -5 degrees Celsius to 120 degrees Celsius. So if I just draw a diagram to show what is happening, start at -5 degrees Celsius, and as I have heat being applied to this system, my temperature raises. And then once I hit 0, which is my melting point of water, there's still heat being added to the system, but my temperature isn't raising. And that's because all of the energy or heat that is being given to the system is going to break those intermolecular forces that are keeping water as a solid. And as those get broken, then the water is now liquid water. Once that happens, the temperature that can then continue to raise as there's more heat added, and that is until 100 degrees Celsius. At that point, all of the energy that's being given isn't going to change the temperature because it's going to be going in to convert from a liquid to a gas. And then once those intermolecular forces are broken and water is a gas, then once again the heat or energy that's being applied to the system can go to raise its temperature. And here that ends at 120 degrees Celsius. So we have 5 different sections here. We have the section where it's a solid going from -5 to 0 degrees Celsius. Then we have a section where the temperature doesn't change. So this is the latent heat of fusion, where we are changing from a solid to a liquid. Then we have another section over here where we have a temperature change as a liquid, then converting from liquid to gas, so latent heat of vaporization there, and then as a gas, increasing in temperature. So we have 5 different sections. So we're going to split our calculations into those 5 different sections. The mass is going to be the same for every single one. The 2 state changes don't involve a temperature change. And the other 3 sections, so as a solid, as a liquid, and as a gas, we have temperature changes from -5 to 0, from 0 to 100, and from 100 to 120. So we'll go through those calculations. So section A was from -5 degrees Celsius to 0 degrees Celsius. So that was its increase in temperature as a solid. So the mass was 60 grams. the specific heat capacity of solid water or of ice is 2.00 joules per gram per degree Celsius, and our temperature change ended at 0, started at -5. So we had an increase of 5 degrees Celsius. So the amount of energy to increase 60 grams of ice from -5 degrees Celsius to 0 degrees Celsius and plugging that in, I get 600 joules. I'm going to convert that to kilojoules by dividing by 1,000, so 0.6 kilojoules for section A. Section B then is as I'm going from a solid to a liquid. So for water that happens at 0 degrees Celsius, so I have no temperature change here. So my mass is still 60 grams. My latent heat of fusion, so how much energy is required to raise 1 gram of a substance, to change 1 gram of a substance from a solid to a liquid for water is 333.55 joules per gram. And those are given to you in the document that I posted for practice questions on the hub. So here our energy is just equal to our latent heat of fusion times our mass. And that is equal to 20,013 joules, or 20.013 kilojoules. So for section A, we had 0.6 kilojoules. For section B, for the state change, we had 20.013 kilojoules. And then the next section was as a liquid going from 0 degrees Celsius to 100 degrees Celsius. So once again, mass is still the same, 60 grams of liquid water now. Specific heat capacity of liquid water is 4.19 joules to raise 1 gram of a substance by 1 degree Celsius. And our delta T was 100 degrees Celsius. So the amount of energy for that then, Q equals MC delta T, 60 times 4.19 times 100, which is equal to 25,140 joules, or 25.1 kilojoules. Okay, so we're going to need that guy later. And section D then was going from a liquid to a gas, which for water happens at 100 degrees Celsius. So 60 grams of water, and the latent heat of vaporization for water is 2,260 joules of energy for 1 gram of water to be converted from a liquid to a gas. So the amount of energy there then, the latent heat of vaporization times mass, which is equal to 135,600 joules, or 135.6 kilojoules. It's another number we're going to need at the end. And then the last section was going as a gas from 100 degrees Celsius to 120 degrees Celsius. So the 60 grams of gaseous water, specific heat capacity for gaseous water is 2.02 joules per gram per degree Celsius. and our change in temperature is 20 degrees Celsius. So for that section, our energy 60 times 2.02 times 20, which is 2,424 joules, or 2.42 kilojoules. So for that entire system to go from -5 degrees Celsius to 120 degrees Celsius, my total heat is equal to the heat at each of those different sections. So we started with going from -5 to 0 degrees Celsius, and it took 0.600 kilojoules for that. Then it was 20.013 kilojoules of energy to convert that 60 grams of water from a solid to a liquid. And then to raise that liquid from 0 degrees Celsius to 100 degrees Celsius was 25.1 kilojoules. Converting the 60 grams of liquid water to 60 grams of gaseous water took 135.6 kilojoules of energy. And then our final amount was 2.42 kilojoules of energy to raise the temperature from 100 degrees Celsius to 120 degrees Celsius. So our total is 183.7 kilojoules of energy that it took to raise 60 grams of water from -5 degrees Celsius to 120 degrees Celsius. Okay, questions for you guys to practice in your textbook on page 281, questions 1 to 10. And then in the hub, there is a Word doc 2 pages long with some heat calculations in there.